Before I started talking about acid mine drainage, I'd like to introduce to you water servicing technologies and some of the scopes we are working on. We are a team of hydrogeologists, engineers, numerical modeling specialists, and scientists. And our main goal is to offer practical and economical solutions to meet demands related to groundwater, geochemistry, geotechnics, and environmental data management. We offer consulting service as well as technologies through software, sensors, and the development of customized solutions to meet the most diverse challenges. We also offer training courses, webinars like this one, and workshops. This is our service and areas of expertise: hydrogeology, data management, hydrogeotechnics, and geochemistry, and some of our current clients. We have a brief summary of our talks today. First, we will talk about the acid rock drainage elements, and then about the chemical elements and mineralogical assemblage, diagnosis, monitoring, and finally, a little bit about modeling. Acid rock drainage is formed by natural oxidation of sulfide minerals, which are exposed to the air and water. It means to atmospheric conditions. Excavating sulfide containing rocks accelerate the oxidation process and increase the exposure of sulfide minerals to air and water. Sulfide minerals are common in gold, copper, coal, uranium mines, for example. The most common characteristic of acid rock drainage is the low pH. It means acid pH. So it could start close to 7 and will be reducing through the time. Another characteristic of the effluent is the moderated to high concentration of metals, high concentration of sulfates, and high electrical conductivity and high suspended solids contents. For the acid drainage generation process, we need to have 3 reagents: water, sulfide material, and oxygen. Sulfide material becomes available through mine excavation process. And we have the atmosphere and as an infinite reservoir of oxygen. And in the next slides, we will see that we don't need a large amount of water for acid rock drainage producing. So once we have the sulfide exposed to these conditions, we have its oxidation. Here we have the reaction of pyrite of oxidation. The oxidation of sulfide promotes initial reduction of the pH of the medium around 5 and 6. And this pH is favorable for the performance of iron oxidizing bacteria. So the oxidation of iron 2 to produce iron 3, which is more effective to oxidizing the pyrite, for example. So the iron 2 produces the pyrite oxidation reaction, either by oxygen or by iron 3, will oxidize to produce more iron 3. So therefore, once started, the acidity generation process can't be eliminated. It is recommended that a diagnosis program should be carried out from the beginning of the mining activities associated with with a mining plan. Well, the neutralization of acidity occurs by the neutralization with carbonate minerals, mainly calcite. The neutralization process precipitates siderite, as we can see here, which eventually can be solubilized in the acid medium and produce ion 2. So this ion 2 can produce this ion 3, and so, and the process of oxidation is continuous. So here we have the stage of acid rock drainage formation and neutralization. So in the beginning, if we have calcite, the calcite maintains the pH around 6 and 7. And once it is consumed, it precipitates siderite. And siderite will control the pH, but around 6 and 5. And this process will take a pH around this for a while. And at this pH, the element is applied to the aqueous phase. It's assumed that calcite can precipitate. And also the oxidation of ion 2 to ion 3 can be lead to the precipitation of oxide hydroxide of ion as goethite. So the pH becomes lower and lower until the acidity is high enough, around 3, to solubilize aluminum silicates. So the alkalinity generated by these minerals are not enough to control the pH. So now we are going to talk about the chemical elements and mineralogical assemblage. Here we have the interface of the occurrence of lithophiles, chalcophiles, and siderophiles elements. And as you can see, lithophiles are common, the crust, and siderophiles are common in the inner layers of the mantle, close to the core of the earth. The geochemical affinity between them explains the occurrence of sulfide minerals in the deposits of iron and, for example, gold, silver, copper, uranium, coal, and uranium. So, and associated to these commodities, we have also some another concern elements are arsenic, lead, and so to extract these minerals, these elements, a large volumes of rocks rich in sulfide minerals are exposed to atmospheric conditions, and more than 90% of digged materials is discharged as tailings or classified as waste rock. And its geochemistry is very similar to the minor rocks. And the sulfide minerals are unstable under oxidizing condition. And this exposure to the atmosphere and oxidized water, it means rainwater, results in the mineral dissolution and potential acid drainage and metal mobilization. Here we have the geochemical data for mineral constituents and mine drainage associated with sulfide deposits. So as we can see, the concentration in aqueous phase of mineral and trace elements as cadmium, cobalt, copper, nickel, lead, and zinc will increase as soon as the pH decrease. So this is why we have also not only the acidity, but also the metal leaching. This is our main concern. This is the conceptual model for pyrite oxidation. The sulfide particle, for example, this is a pyrite, for example. The sulfide particle has a solid surface, and the oxidation process takes some time to start to react. Along the time, microtubes are formed in the outer layer, like this. And these microtubes facilitated the diffusion of oxygen on the mineral surface. This layer is named ash layer, and this inner region is the reaction front. So then, even the dry period, the sulfide materials is being oxidized, and the ash layer contains the oxidized material. As we saw in the previous slides, water is not a limiting reactant in this reaction. Therefore, the acidity will be stored in the ash layer of the particle until the first rain event. In the beginning of the rain season, the ash layer is washed away and peaks in acidity, for example, and electrical conductivity could be detected. And this model can explain why low sulfide contents material can generate acid rock drainage. The acidity is regarded to metal hydrolysis and the content of the ash layer. So now we are going to talk a little bit about diagnosis of acid rock drainage potential. So this static assays presents the sample conditions in a very specific time. Therefore, no speculations can be made about its future. These tests are useful for estimating the acidity generation potential and the conditions to which this material will be submitted, disposal in waste rock piles or in tailings will answer to the generation of future acidity. Future prediction can be made through kinetic tests and numerical modeling. So here we are talking about these tests, and we have also physical analysis that are very important and about the mineralogical characterization, but we will not talk about this in this webinar, maybe in a next webinar. So the raw rock analysis is important to determine the main elements that sorry, the elements that make up the sample. This analysis is carried out by means of a strong acid digestion, where almost all the constituents are solubilized. And we have the analysis of soluble constituents. And in this analysis, a partial digestion aims to simulate the constituents of the sample that can be leached to the environment. The fact of some elements exist in the sample does not mean that they become a contaminant. Here we have two methods that we use in general: the EPA 3050B and the EPA lift methods. So the first test is the acid-base balance. In the acid-base balance, we can see that to neutralize the acidity generated by the pyrite, we need twice amount of calcite. Here, 1 mole of pyrite. 2 is neutralized, produce 4 moles of H plus, and to neutralize the H plus, we need 2 moles of calcite. And this test is based on this both reactions. The acid drainage generation potentials is based in the sulfide content in the samples. And the main objective is of the sulfur analysis is to identify the nature and the concentration and the composition of different mineral sulfur species. With precision and accuracy, this analysis is important to predict the potential for acidity, as I said, and the leaching of a trace element under weathering conditions. Here is some of the main sulfide minerals. So we have pyrite and marcasite. And pyrite and marcasite have the same molecular formula, but only pyrite can generate the acid rock drainage. We have the copper sulfates as chalcopyrite and chalcocite, sphalerite, galena, and the pyrrhotite and arsenopyrite that are very common in the mining process. So, as we saw in the previous slides, the drainage pH becomes acidic only when the neutralizing minerals are depleted and the neutralization rate is not enough. Only a few types of carbonate react fast enough to keep the drainage in the pH around the neutral, and these minerals are mainly calcite and dolomite. Magnesite and ankerite contain iron in the composition. The presence of iron is not desired, as iron 2 can be oxidized to iron 3. As seen earlier, iron 3 acts as a strong oxidant. The neutralization potential generated by magnesite and ankerite is consumed by itself. Therefore, these carbonates are not effective in neutralization in the neutralization process. One of the parameters that we have with the test is the NPR, which is the ratio of the neutralization potential, NP, to the acidity generation potential, AP. As we saw in the reaction stoichiometry, we need at least twice more neutralizing material amount. It's important to emphasize that neutralizing and acid generating materials must coexist in time and space. This may be obvious, but it's because if the material is exposed in a condition where the carbonates are solubilized and for example, and the sulfide materials are in a reducing conditions. So in the future, we will have the sulfide materials and the carbonates and the neutralizing material has gone. Chances of generating acidity are not reduced when the amount of neutralizing materials is 4 times greater, as we can see here. So if we have three more times neutralizing material, I have a very low chance to have acid rock drainage, but it is not very confident. So well, another static test is the net acidity generation test. It's known as NAG test. The objective of this test is to evaluate the capacity of a sample to neutralize acidity produced by the sulfide oxidation. In this proposed, the sample is oxidized with hydrogen peroxide, and this test aims to a better understanding of the acid drainage generation potential of a specific site after previous study of carbonate and sulfides contents in the sample. Well, we really need to know the sample and the materials that we are working. So we can plot the results of the acid-base balance and the net NAG results. So we have here another parameter from the ABA test, ABA test, and the NNP is the difference between the material with neutralized content and the acidic material. So we have more neutralizing material and NPR higher than 1 and a NAG. Oh, sorry, I didn't say. At the end of the test, we have of the NAG test, we have the NAG pH, which in other words, the acidity generated by the oxidation of sulfides. If we have a NAG pH less than 4.5, that means that we can have acidity generating material. Therefore, the classification of acidity generation potential of material must be done considering more than one type of test as the results are complementary. So now back to the table. So if we have an NAG pH above 4.5, NPR higher than 1, and NNP higher than 0. So probably we have a no acid form material. If one of these conditions is not satisfied, we have a material with acid, the potential for acid forming as uncertain. And the materials, so with NNP lower than 0, NPR lower than 0, and night pH lower than 4.5, so we have a potentially acid generation material. Well, we are often asked about the sulfide content that can generate acid drainage. My answer, as a good consultant, is it depends. Here we can have a material with a 3% of sulfide down here, and it may or may not generate acidity. On the other hand, we also have a material with less than 0.1% that is the static tests are inconclusive. So the sulfur content cannot be used as a unique criteria for evaluating the potential for generating acid drainage. Here we have the pH, the paste pH, the pH analysis. This is a good test. It's a very cheap test. For instance, we can estimate the weathering level of the sample. And the method consists of washing the sample. And it indicates the presence of reactive carbonates and the acidity generated by methyl hydrolysis. This pH analysis is analysis of the ash layer that we presented in the conceptual model of pyrite oxidation, the unreacted core model. So here we have the kinetic tests, the samples. Let me back. The samples classify as uncertain. The samples could be submitted to kinetic tests, and the kinetic tests establish the relative rates of acid generation and neutralization. This is important to determine whether a sample will be acid. Indicates the probable period when the acid production can be started, and also estimate the hydrogeochemistry and metal load of the drainage. With kinetic tests, I can say about the future of the sample. These tests are important because you will consider the secondary minerals, for example, and the chemical drainage, the content of the chemical drainage. So the kinetic test aims to accelerate the weathering, dissolution, and precipitation process of minerals. And this can be used to estimate the reaction rates. The test terms can be relatively long, about 1 year, for example. It means high costs. and also mean that we need to reduce the number of cells. So when we carry out this test, we selected the samples that will to be submitted to kinetic tests. So the chemical composition of drainage depends on the reaction with primary minerals and the dissolution precipitation of secondary minerals, as we saw, the siderite and the hydroxyl aluminum and hydroxide and oxide of iron. So these are very important questions about kinetic tests, which methodology protocol to execute, how long it test will run, the parameters, what type of cells, how to interpret the results. So these are very important questions. It's very important is always to perform the mineralogical characterization. We have to ensure that to carry out a kinetic test, we have enough mass of the material, and that the material is representative from the site. So we need also to run a QA/QC program. So we are talking a little bit about the monitoring of drainage in different phases of the mining project, when and how. This is because it's common that the company execute only the environmental monitoring. And one of the most important lessons that has been learned by mining is that monitoring should be started as soon as possible. In the exploration phase in the beginning, because we have some geochemical exploration tools that can be used in the future. So techniques applied for exploration geochemistry studies can be used in the baseline and background studies that can support in the future of the monitoring. We have the preoperational monitoring. So we really start, we can establish a net of monitoring of the hydrochemical soil and water quality before the mining operation. So, and the stage of commission and mine operation, we are talking about about controls. This is the longer. I don't know if I can say longer, but it's a longer period of activity compared with the previous one. And in this phase, we have the highest risk to the environment, because we need to control and monitoring hazard and reagents. For example, mining gold, mine process, we need cyanide, so we need to control this. We need to have compliance with legal requirements, and we have structures as pit, dams, piles, and processing plant. So we need always to prevent and diagnose. In the end, we have the decommission and mine closure. Mine closure should not only be considered in the final phase, in the end of mine, but closure should be considered and from the beginning. So this is an important lesson also learned by mining. So if we have a baseline stud, background stud from the earlier periods of the mine project, we can establish the specific objectives and parameters to be controlled in the mine. Finally, we are talking about the hydrogeochemical modeling. So I will show you some examples that of the projects that we are working on about in simulating current scenarios and post-closure scenarios. So just talk a little bit about hydrogeochemical modeling and about numerical modeling. We have the input data. So the user must insert the parameters defined in the conceptual model here. So we have the calculation, and some softwares, this calculation is like a closed box. So we don't understand very well, or the software, we cannot be only a software operator. We need to understand what the software is doing. So in this step, the software will process the input data using the equilibrium equations available in the database. This is specific for hydrogeochemical modeling. And so we have the output data. This is very simple, as we can see here, but we need to understand what type of calculation the software is doing to understand the output data. So we need to know very well the input data. Doesn't matter how good our computer is. If it's fed by bad data, we will get bad predictions. This is why I need to be very confident in the data before I start to run numerical modeling. This is an example. This is a tailing dam. So in the current scenario, we have saturated tailings. We have some contact with the aquifer water, with the groundwater. Then the effluent, it means the drain outlet, it's a mixture of aquifer water and the percolated effluent. So in this case, the current scenario, maybe the tailings, the tailing then is not generating acidity, because we have a chemical equilibrium with interstitial water. So we have maybe a reducing medium, and we have a lower contact with the partial pressure of O2. So maybe we will not have acidity in the current scenario. So in the future scenario, we have part of the tailings in the insaturated region here. So we have the contact with the atmospheric conditions. And this material is percolated by rainwater and in equilibrium with atmosphere, which means we have maybe the acid production. The drain outlet will remain as the mix of the aquifer water and percolated effluent. So this time we have a oxidized region right here, And this exposure of the tailings can change the chemical drainage. So in the modeling, we can use the block model of transport. It will simulate it. It is one dimensional model. We can simulate n number of cells, and the water from we have initial water here in, as I said, in equilibrium with the atmosphere. We have the equilibrium with atmosphere and with the interstitial water here. So the rainwater will fill itself for, in that we name shift. And then we will have in the dam bottom a low O2 content. This is for a current scenario. So in fact, this pH could be okay. It means it's about 5 and 6. It can be stable. We are talking about pore volume. Pore volume means each time that the water start in the cell 1 and finish to percolate the cell N. This is a pore volume. When the water completely run the column. So in 2 to 4 pore volume, we have a pH around 6. That's fine, but it's not completed, because when the effluent reaches the drain bottom, and the drain bottom is partially drowned, so we have a relatively higher O2 content. It means that some minerals will be precipitated as iron oxide and iron hydroxide. And the precipitation of iron will reduce the pH. So we have the pH around 2, and we could be stabilized around 3 or 4 through the long of time. So we need to model this type of reaction, and how we deal with this pressure of CO2 and O2 in these structures is not a trivial issue. We need really to understand the process. Well, here sorry, this is in Portuguese, but it's depth. So we have here the surface and the ground, in the deep ground. So here we have the unsaturated region. So acid pH around 2 for the first pore volume. As we can see, this line represents the initial stage, and this one, the first pore volume. This occurred due to exposure of sulfide to oxidizing atmosphere, forming sulfuric acid here. So in the saturated region, although there is an influence of water coming from the upper part of the column, the pH remains close to 5 in the first pore volume. So when we reach the saturated region, we can have the pH around 5 here. And after a longer period of time, when the sulfides are consumed, the pH stabilizes around 6. We have here the pore volume like 10 and like 5. We have the stabilization of the process. One question or an issue that we have at we need to have we need to know the hydrodynamics parameters of the structure of the tailing dam or the waste rock pile. So we need to know, because it's very difficult to consider the anisotropy in the hydrogeochemical modeling. Well, we can do that, but it's not only with a hydrogeochemical modeling. Maybe we need to do a hydrogeochemical modeling and also a hydrogeological model together. So in a brief experience that we have with numerical modeling, we have learned very important lessons, and I will present some of these lessons for you. And the first one is that the hydrogeochemical and mineralogical characterization data must be deeply analyzed and revealed, because this is our main information. It's like a footprint that this data will show us and will conduct us to do a right conceptual model. That is the next lesson. Conceptual models must be thoroughly discussed by an interdisciplinary team. So conceptual model is a puzzle. So we have a lot of pieces, and we have to put each piece in the right place, and the piece together will make sense. So we need to have an interdisciplinary team. Then another lesson is about experience. So no one better than the site's employees. More experienced employees can provide important information. So we need to chat and share our ideas, our knowledge, and learn about the site. So do not restrict your analysis to environmental data. So people get confused and understand that acid mine drainage is an environmental problem, but it's not. So we need to get involved in the mining planning, the geologists, and so the engineers of the processing plant. So we need the whole data, because this data should be used and considered in the conceptual model. So the whole company's area must be involved in this process. And the implementation of the numerical model comprised less than 10% of the effort when the previous steps have been completed. This is a very, very important, because maybe we can be anxious to start to model numerically, and sometimes we can jump or shift some steps. And the most important lessons is numerical model won't give you answer about things you don't know. So if you want to know about for example, if you want to know about the specific mineral solubilization, you need to know very well this mineral. You need to know thermodynamic data. So that's all. I appreciate your patience and thank you all for watching this webinar.